Hello all, this is Mr. G and this is our warm-up for today's lesson. So pause the video right here, give these problems a shot, come back when you think you have an answer. We're going over in 3, 2, 1, let's go. Number 1, it says simplify each expression and it's the square root of 16. Okay, well that's just 4 because 4 times itself gives you 16. You might have been tempted to put plus or minus 4, but you actually don't need to do that. You only need to worry about the positive or negative, the plus or minus answer when we put the square root there. So like if we take the square root of both sides of an equation to get rid of a power of 2, then we need to worry about the positive or negative. But here, since the square root's already sitting there waiting for us, it's actually called the principal square root, and we just worry about the positive answer. Now, number 2, square root of 12, is a little bit more difficult. 12 is not a perfect square, unlike 16, so it's more difficult to take the square root, at least in our head. I mean, it's going to be 3 point something, 3.5 maybe, I don't know. But basically, we don't want a decimal. We don't want to round it. So what we want to do is we want to leave this in exact form, meaning we want to find two numbers that will multiply to get to 12, where one of them is a perfect square. So 4 times 3 would be what we want to pick. I mean, you also could have written it as 2 times 6, but this is not going to be helpful. Even though 2 times 6 equals 12, neither 2 nor 6 are a perfect square. But in 4 times 3, we can take the square root of that 4, which will give us an exact form. Let's see, the square root of 4 is 2, and the square root of 3 is just the square root of 3. There we go. So 2 root 3 is our final answer for number 2. Let's take a look at our objective. So today we're doing chapter 4, section 8. We are finally on the last section in this chapter, chapter 4, which seems like we've been in for like ever at this point. But unfortunately, 4-8 could be an entire chapter just into itself, this one section. Anyway, let's not waste any more time. After this video, we should be able to simplify non-real numbers. That's our goal. So we're actually learning about a new type of number today called a non-real number. So before we get into any problems with numbers, let's just try and think of, okay, what are some types of numbers that we know? So I want you to pause the video here and try and come up with an answer to this. What types of numbers do you know? Make a list. So pause the video. We'll go over the answers in a second. 3, 2, 1, let's go. So what type of numbers do you know? You might have been able to come up with positives, like positive versus negatives, or like integers, or evens, odds, negatives. These are just some different possibilities. I'm sure you probably had more than I'm listing right now. But what I'm going to do is I'm going to present sort of a Venn diagram of all the different categories of numbers that you should know, or at least every number you know at this point is represented somewhere on this map. Like natural numbers, the one that's inside the most circles right down here, natural numbers, those are like the first numbers you learn, like 1, 2, 3, and it keeps on going. The counting numbers, sometimes they're called. Now that's a subset. Subset meaning it's a group inside another group. The natural numbers are inside the whole numbers, meaning every natural number is already a whole number. The only number that would go, the only whole number that's not a natural number is 0. So the whole numbers are 0 and all of the natural numbers. Then we have another bigger group, which is called integers. Integers, again, the whole numbers are inside the integers, so the whole numbers are a subset. So, 0, 1, 2, 3, those are already integers. But integers also include like -1 and -2 and -3 and all the negatives going on all the negative whole numbers, or the opposites of whole numbers, I guess we could call them. And then above that, we've got rational numbers. So now we've got some decimals and fractions. So like 1/3 or 0.3 repeating. You could also have like 5/4 or maybe like 0.5. Those are all examples of rational numbers. Then we've got this group over here, irrational numbers, that are completely separate. So these are irrational numbers are not subsets of rational numbers, integers, and none of those groups, none of those numbers belong inside irrational numbers. Irrationals are completely separate from rationals. That's why they're called irrational numbers. And the most famous example is pi, and that's because pi is approximately 3.14159, and it keeps on going. What makes it irrational is that it never repeats and it never ends. You see irrational numbers a lot with square roots, like if we took the square root of 3, like if I plug that in over here, second square root 3, we get an irrational number, a non-repeating, non-terminating decimal. So those are irrational numbers. But actually, all of these numbers are another type of number. So there's one name that covers all of these types of numbers, and it's reals. These are all real numbers. So we can also organize it like this. So we have this box representing real numbers, and all of the other ones we just talked about as a subset of real numbers. They're different type of numbers, but they're still real numbers. Now you'll probably notice there's this category over here that is separate from real numbers. And that's what we're going to be learning about today. Numbers that are non-real numbers, which we call imaginary numbers. Imaginary numbers. Now, this is a really unfortunate name that they're called imaginary numbers because some people are able to look at this and be like, well, if it's imaginary, why do I even need to worry about it? It's imaginary. It doesn't exist. And it's just kind of unfortunately ignorant like way to look at things. I can get why you look at that, but it's just well, let me put it this way. Here's a lesson from math history. Okay, you don't want to be a bozo, all right? And what I mean by you don't want to be a bozo is basically um, a lot of times throughout history, there's been like a new type of number that came up that we just sort of take for granted at this point. But back when it was first not invented or discovered or first started to be used, people were like, oh, well, that number doesn't exist. Like, for example, for most of human history, people did not think the number zero existed. The number zero didn't start showing up till, depending on which source you use, like, 3 BC or like 4 AD, or some people even say, I think it was in India in like 600 or something like that. I'd have to double check my dates there, but it's something like that. So that means for all of the history before then, people didn't think the number zero existed. Yeah, they count to one, two, three, four, whatever, but they didn't have a number to represent zero. So you don't want to be one of those people saying, "Oh, that number doesn't exist," just because it's new or something like that. Not that imaginary numbers are new, but we're just learning about it, so it's new to us. All right, so now let's take a look. Oh, right. So before we jump into like when they show up, it's understandable for someone to say, "Okay, but why do we need them? Why do we need this new category of imaginary numbers?" And basically, just like any new type of number we learn, this new type of number is going to help us solve a different type of problem, help us sort of get around a math problem that up until now was sort of a like a wall. We couldn't get past it. It was a stumbling block, we could call it. Now let's take a look at a fairly simple equation. We've got x squared plus 1 equals 0. I mean, this is not that complicated. We should be able to come up with an answer to this. I mean, it's x squared, we've got a power of 2, we've got a plus, and we've got a 1. None of this is too complicated. We should be able to come up with something. Let's solve here. We got to get x by itself, so we take away 1. Then we get x squared equals negative 1. And then to get rid of that power of 2, we take the square root of both sides. So we get x is going to be equal to plus or minus, since we took the square root of both sides. And then we're sort of stuck because the square root of negative 1, we cannot do that. Like, it's not going to be 1 because 1 times 1 equals positive 1. And it's not going to be negative 1 because negative 1 times negative 1 gives us positive 1 again. There's no number that we can square, at least no real number that we can square that will give us a negative 1. So up until this point in our mathematical careers, at this point, we just sort of had to tap out and be like, all right, I guess there's no real solutions. We cannot go any further with this problem. But today, we're going to get around that using the imaginary unit. We're going to find a way to express this square root of a negative where it's like, okay, we don't know exactly what this number is because it is a non-real number. It doesn't fit into any of the other categories. But let's come up with a way to express this so we can sort of not just stop at that point and keep on going and actually solve the problem, or at least represent a solution to the problem. So let's take a look at the definition. The imaginary unit is the solution to the equation x squared equals negative 1. The solution to x squared equals negative 1. Now, there's a few different ways to express this, or to think about this, I should say. One right here, this is the more important one. If you're only going to remember one thing about I, the imaginary unit, make it this. I, the imaginary unit, is whatever number where when we square it, it equals negative 1. I squared equals negative 1. That's the most important thing to remember about I, this imaginary number, this most basic imaginary number. Now this one over here, I equals the square root of negative 1, it's pretty much the same thing, but it's not as helpful. If you're only going to remember one, make it this one over here. I squared equals negative 1. But basically, anytime we're trying to find the square root of negative 1, we can use we can use the imaginary unit to represent that non-real number, and then we can continue the problem. Let's take a look at some examples. So example 1, we have to simplify the square root of negative 9. Well, we can't do that, at least not using a real number, because the square root of 9, we cannot take the square root of. Now, We saw something sort of similar to this earlier in the warm-up. I forget exactly what the number was. I think it was like the square root of 12 or something like that. And we could not take the square root of that number because 12 was not a perfect square. So what we did is we wrote it as two numbers that were factors of 12, where one of them was a perfect square. So essentially, that's what we're going to do here. We're going to rewrite this negative 9 so that it's, how do I want to say this? We're going to rewrite it as two factors of negative 9, where one of them we can take the square root of. So what I would do is I would just write the square root of negative 9 as the square root of positive 9 times negative 1. Because 9 times negative 1, that does equal negative 9. So we did not change this expression, but now all of a sudden we have a perfect square that we can take the square root of. So let's think about this. The square root of 9, that would just be 3. And then the square root of negative 1, well, that's just the square root of negative 1, but we're not going to leave it like that. Because remember, whenever we have a negative 1 inside a square root, we can rewrite that now as the imaginary unit, 3i, and that's going to be our fully simplified answer. The square root of negative 9 equals 3i, 3 times the imaginary unit. That's how we're going to represent this moving forward. Let's take a look at B. So we've got 3 times the square root of negative 49. Well, this 3 is okay. I'm not going to do anything with that. And we see a square root of a negative. That means we've got some work to do in that square root. How can we rewrite the negative 49? Well, 49 is already a perfect square, so we can just make this 49 times negative 1. And then, again, we just carry the 3 over. 3 times the square root of 49 is 7. Remember, that's why we picked that 49, because it was a perfect square. I guess we didn't really pick it, but it made it easier since it was a perfect square. And then the only thing left inside the square root is a negative 1. And we can simplify this. 3 times 7 is 21. And the square root of negative 1, that's I. That's our imaginary unit. That's how we're representing that square root of negative 1. So we're not just stuck with a non-real number. We've got, okay, now it's I, the imaginary unit, that we can actually use when we're moving on. Or we can move on with it, I should say. All right, let's take a look at C. Square root of negative 17. Now this one has me a little concerned. Well, first let's deal with the negative. So let's rewrite this as the square root of positive 17 times negative 1. I don't see, like, this 17 is not a perfect square, and I don't see any perfect square factors of 17. 17, I believe, is prime. So we can't do anything with that. So we could write it like this, just the square root of 17 times the square root of negative 1 we know is I. But I'm going to put the I in front just because I don't want it to accidentally, so that's going to be the final answer. The reason I put the I in front is I don't want anyone to accidentally draw their square root further than it should have gone or farther than it should be. And then it looks like the I right here is inside the square root. So that's why I always put my I's in front. If you don't want to do that, that's okay, but I think that's the best way to do it. All right, one more on this slide. So we've got the square root of negative 108. Well, first let's get that negative out of there. Well, not out of there, but sort of, let's factor it out, I guess we could say. So it's 108 times negative 1. And then 108 has got to have a perfect square factor. I think 4 is going to be a factor, but I bet there's going to be a bigger one than 4. Let me just go to the calculator. So 108 divided by 64 is going to be too big. I don't think 49 is going to go in. I'll check it, though. No. So then 108, what would be next after that? 36. I always like to start from the bigger of perfect squares and work my way down. Oh, 3. Good. So we can rewrite this as the square root of, 36 times 3 times negative 1. Sort of running out of space, so I'll jump down here. The square root of 36, that's a perfect square. That's just 6. The 3 is still going to be inside the square root, and the square root of negative 1 is I, but I'm going to write it as 6I root 3, just so the I doesn't look like it's inside the square root, and that's our final answer. All right, let's take a look at this one. So example 2, I want you to try A and B on your own. Try to simplify these two expressions. So we're going to go over the answers in 3, 2, 1. Did you pause it? Did you try it on your own? All right, let's go over the answers. All right, A. Let me see. So it's negative 2 times the square root of negative 25. Negative 2 just comes over. Well, this is just 25 times negative 1, because 25 is already a perfect square. So that's negative 2 times the square root of 25 is 5, times the square root of negative 1 is just square root of negative 1. And then I'm going to need some more space. Negative 2 times 5 is negative 10, times the square root of negative 1 is I, the imaginary unit. So negative 10I is our answer for A. Let's take a look at B. So we have 5 times the square root of negative 320. Again, the 5 is okay. So it's 5 times the square root of 320 times negative 1. Let's just factor out the negative first. And 320, I'm betting that, well, I think it's divisible by 4, but I bet there's one bigger than it. So 320 divided by 64 might work. 64 times 5, just got lucky there. So 64 times 5, and we can't forget about that times negative 1. And then let's see, what would this become? I actually don't want to put my answer or my work over there. Let's keep going vertically. So then it's 5 times the square root of 64 is 8, times the square root of 5 times the square root of negative 1 is I. And 5 times 8 is 40. And let's bring the I in front of the, that doesn't really look like an I. Let's bring the I in front of the square root of 5. So 40I times the square root of 5, and we are finished. Hopefully this made sense. As always, if you have questions, let me know. Enjoy the rest of your day.